Before an earthquake shakes the ground, something sneaky might happen first. A slow, quiet movement with no shaking at all. No one is aware that right under their feet, the land is preparing to tremble violently, wreaking havoc, bringing destruction and devastation. A new study shows that such a slow creep might be how earthquakes begin. To figure this out, scientists didn't start with giant pieces of the earth. Instead, they went into a lab and used clear plastic sheets called plexiglass. They pushed two sheets of plexiglass sideways against each other, just like how tectonic plates, huge chunks of Earth's crust, push against each other underground. As they pushed, the plastic cracked, kind of like what the Earth does during an earthquake. And even though it was plastic and not rock, the physics, the way things break and move, was the same. Earthquakes happen when two tectonic plates try to slide past each other, but they get stuck. The edges between them don't move easily because of something called friction. It's kind of like when your shoes grip the ground. Over time, the plates keep trying to move and stress builds up. Think of it like bending a stick. At first, it doesn't break, but if you keep pushing, it will eventually snap. The spot where the plates are stuck is called a fault, and there's a thin, brittle part in that fault. By brittle, I mean that it doesn't bend, it just breaks. Here's how it happens. First, a tiny crack forms. It's small and moves slowly. There's no shaking yet, but something is already happening under the surface. The crack spreads, building up more energy. When it finally reaches the edge of the brittle zone, boom, it speeds up, suddenly racing forward really fast, almost as fast as sound, and that's when the Earth starts to shake. So scientists decided to find out how that very first crack starts. They conducted their experiment, whose setup was similar to a type of fault in the real world called a strike-slip fault, like the San Andreas Fault in California. Even though the materials, plastic versus rock, are different, the way cracks form and move is exactly the same. The experiment has helped scientists understand that earthquakes don't always start suddenly. Sometimes there's a slow, quiet start, like a warning sign before the big quake. This early stage of an earthquake is called a nucleation front. It's like a seed of a crack, gently creeping through the material long before any actual rupture happens. This quiet and slow movement doesn't release energy into the surroundings. At first, scientists thought of cracks as simple one-dimensional lines, like a straight tear in paper. But something didn't add up. The slow-moving nucleation front wasn't behaving like a normal, fast-moving crack, and it wasn't clear why or how it suddenly sped up and became an earthquake. The answer came when scientists realized they had to think in two dimensions instead of one. Instead of imagining the crack as just a fine line, they began to think of it as a patch, like a growing circle, that starts at the surface where two materials touch. As this patch spreads out, more material along its edge has to break. The important thing here is that the energy needed to break the material is related to how long the patch's edge, or perimeter, becomes. The bigger the perimeter, the more energy it takes to keep breaking. That's why this patch moves slowly at first. It doesn't yet cause the violent shaking we associate with an earthquake. Because it moves without sending shaking waves, this stage is called aseismic. Eventually, the growing crack patch spreads beyond the special brittle zone, where the materials are stuck. Outside this zone, the energy needed to keep breaking the material doesn't increase anymore. Instead, there's now extra energy building up, more than what's needed to keep the crack growing slowly. This extra energy doesn't stay quiet. It suddenly powers the crack to move much faster, turning it into a full-speed rupture. That's the moment when the earthquake begins, and the ground starts to shake. These findings help explain how earthquakes might start off slow and silent before quickly turning dangerous. They show that small, slow cracks can suddenly transform into powerful, fast-moving ruptures if the conditions are right. Scientists believe that they can learn to detect the aseismic stage before a crack speeds up. It might one day be possible to predict earthquakes, or at least understand the warning signs better. Now, even though earthquakes are only the third most common type of natural disaster, they cause the highest number of fatalities. NASA plays an important role in studying earthquakes by using satellites that orbit the Earth. These satellites collect data and images that show how the ground changes after an earthquake. For example, they can detect when the land shifts, rises, sinks, or cracks. These surface changes help scientists learn more about the strength and impact of earthquakes. NASA's satellites can also track changes in nighttime lights. If a city goes dark after a quake, that's a clear sign that the area may have lost power and could need help. Now, how about we talk about the most common earthquake myths, like the one about megaquakes? Some people really worry about super huge earthquakes, but there's a limit to how big they can get. The size of an earthquake depends on the size of the fault where it happens. A longer and deeper fault can cause a bigger earthquake. For example, the San Andreas Fault in California is long, about 800 miles, but not very deep, around 10 to 12 miles. This makes earthquakes bigger than magnitude 8.3 on that fault very unlikely. The biggest earthquake ever recorded happened in Chile in 1960. It had a magnitude of 9.5 and occurred on a huge fault that was almost 1,000 miles long and 150 miles wide. Technically, there's no set limit on the magnitude scale, but an earthquake bigger than magnitude 12 would need a fault larger than Earth, which just isn't possible. Now, earthquakes can happen near the surface or deep underground. Most occur in Earth's crust or upper mantle, down to about 500 miles deep. But the deepest ones happen only at subduction zones, places where one part of Earth's crust slides under another. In California, almost all earthquakes happen in the top 15 miles of the crust. One exception is the Cascadia subduction zone in Northern California, which continues up through Oregon, Washington, and Canada. Another misconception is that the ground can open during an earthquake, but usually that only happens in movies. A giant crack opening and swallowing things up during an earthquake is just fiction. In real life, the ground on either side of a fault slides past each other. It doesn't pull apart or open wide. Small cracks or holes can happen during landslides or ground failures, but not along the actual fault line itself. Faults don't open up because if they did, there'd be no friction, and without friction, there wouldn't be an earthquake at all. Now, some people think California could break off and sink into the ocean during an earthquake, but that's not how it happens. The ocean floor is just lower land with water above it. California can't fall in. What's really happening is that southwestern California is slowly sliding north toward Alaska along the San Andreas Fault. The Pacific Plate, which California sits on, is moving about 2 inches per year, about as fast as your fingernails grow. So, in about 15 million years, Los Angeles and San Francisco could be neighbors. And in 70 million years, Los Angeles might be sitting near Alaska. I can't wait. People often wonder whether an aftershock can be bigger than the earthquake itself. Aftershocks are smaller earthquakes that happen in the same area after a larger one. They're like our planet's way of settling down after the main shock. But if an aftershock turns out to be bigger than the first earthquake, then we call the bigger one the main shock, and the earlier one becomes a foreshock. About 5 to 10% of earthquakes in California are followed by a stronger one within a week. It's also possible for 2 quakes in the same area to be about the same size. However, very large earthquakes are rare, so it's even rarer to see 2 huge ones happen close together.